Starting for gravitational potential, we have already discussed what gravitational field is. Okay, so suppose this is a body of mass m and radius r, and we have to find the value of gravitational potential at, let's say, this distance, which is distance small r. Now, what do we mean by gravitational potential? If I say that gravitational field is up to this point, gravitational potential due to a body at a point in the gravitational field is defined as work done in bringing a body of unit mass from infinity to that point. That means I have another body of mass m0 here, and this distance is supposed to be infinity from that body, and if whatever work I have to do in order to bring this body m0 from this point to this point, so gravitational potential is defined as work done per unit mass, because I have already stated that a unit mass of a body from infinity to that point. So work done per unit mass, this is what we mean by gravitational potential. So we need a bit more workspace here, so I am shortening my values, making a small diagram. Let us say we have to find the value of gravitational potential at this distance, which is small r, okay, and currently body, the small mass, which is m0, is currently at infinite distance. This distance is infinity, okay, and this whole thing up to this point, the gravitational field start. That is why in definition we have specially used the word gravitational potential due to a body in the gravitational field is defined as work done in taking this body from infinity, or work done in moving a unit mass of a body from infinity to that point, okay. So work done, this gravitational potential is represented as V, it would be work upon this thing, mass, unit mass. From this formula, before going on to derivation, from this formula I can also find out the dimensional formula, which would be, what is dimensional formula for work? Work is force into displacement. Force is mlt minus 2, displacement is L, m0, that is mass, so m. So I'll be left with L square t minus 2. This is the dimensional formula of gravitational potential. Meter square per second square, right? Have I done anything wrong here? Work is force into displacement. Force mlt minus 2, displacement is length over m. Yeah, it's absolutely right. Now, we have to find the expression for gravitational potential. Okay, what we had to do was work done per unit mass m0. How do we calculate work done? Work done is a simple thing, force into displacement. But the problem with this whole situation is, as soon as the body, suppose the body is right now at infinity, this distance is infinite, right? As soon as the body enters the gravitational field, up to here there will be no work done because the body is moving in absence of any external force. But as soon as this body enters this field, it will start experiencing an attractive force, which is given by F is equal to G capital M small m, which is m0 over this distance, whatever the distance be, square. The thing is, if this force is still a constant, I can easily multiply with force and displacement because we have a straightforward formula. But the force is not constant. The force is increasing every inch, every millimeter, because it is inversely proportional to distance square. If we keep on decreasing distance, the force value will increase, and that is why force is not constant here. So what we are going to do here is, we are going to suppose that the body is currently at this distance, which is x from the center of the body, and a small amount of work is done in moving this body by small distance dx. This is what we are going to do. So what you are going to start with, let dw be small work done in moving the body by small distance dx, right? So work would be equal to F dx, that is dw, and we have considered the body to be at distance x, so F is G m0 upon x square. This is the force which is acting on the body in this direction, right? And small distance is also in the same direction, so both are in the same direction. Cos theta is 0 degree, so cos 0 is 1, so we don't have to use that value f dx cos theta, that is 1. So gm m naught upon x square dx. This is the value of small work done. So total work done would be integration of dw from what to what limit? Distance is changing from, initially the body was at infinite distance. This whole distance was taken as infinity, from infinity and to I am taking this body to r distance. It is the point at which I have to find the value of gravitational potential. So this is from infinity to r. Instead of dw, we are writing g m naught over x square dx infinity to r. Take all the constant out of the integration. This was m naught. So m naught are out of the integration. We are left with integration of dx over x square. What is dx upon x square? This is x raised to power minus 2 dx, right? So instead of this I am writing x raised to power minus 2 dx. And what is the integration of this? X raised to power minus 2 plus 1 upon minus 2 plus 1. That will give me x raised to power minus 1 over minus 1. This thing can be written as minus 1 over x. Minus sign I have written on the numerator side, and x raised to power minus 1 is 1 over x. So this integration becomes minus 1 upon x, right? So applying formula, I will be getting gm m naught minus 1 upon x, or even I can take this negative sign completely out of the integration. The limits are from infinity to r. Now what else we have to do? The application of limits, which is upper limit minus lower limit. So minus gm m naught, upper limit is r minus lower limit is infinity. So 1 upon infinity becomes 0 and you are left with 1 upon r. So the formula for gravitational potential becomes minus this is the value of total work done, not gravitational potential. Total work done becomes minus gm m naught over r, and therefore gravitational potential becomes gm m naught over r divided by m naught. That is what gravitational potential was, total work done upon the mass taken or unit mass taken. So you can cancel out these two terms and you are left with gravitational potential is, we also have a negative sign, minus gm over r. This is the formula for gravitational potential at any point which is distance r from the body of mass m in its gravitational field.